Okay, sir, we're starting then.
Okay.
Okay.
Okay. Good evening, everyone. Welcoming you all to the 17th session of the Vertical 3, which concentrates on practical sessions on open and proprietary softwares. And myself, Giri, one of the coordinator for Drug Discovery Hackathon. So as usual, we have a disclaimer. Please do not share any of your personal details during this online meeting. The Drug Discovery Hackathon official registrations has been started. Kindly also ensure that you register for MyGov account, then only you can go for the registration. And kindly refrain from posting any other greetings because we do not want to miss any important questions, so that we will take up all the questions during Q&A session. And tomorrow at 11 a.m., there will be a session by Abhay Jere in his YouTube channel where he'll be discussing about the registration process, what do's and don'ts that you have to take care on formation of teams and all those things. So please be live so that you can ask questions and get it answered, and you can clarify all your doubts, which will be tomorrow at 11 a.m. in his YouTube channel. So today we have the third session from Schrodinger on induced fit docking, and today we have the speaker Prajwal. And if you wanted to watch any of the previous two sessions of Schrodinger with the code SH01 and SH002, please watch it in the same channel, that is MHRD Innovation Cell. Over to you, Prajwal. Thank you.
Yep. Thank you, Dr. Giri. So I think it's the time to start exactly 6.1. So, okay, I just share my screen. Yep. And it's up. Yep. In the full screen mode. So can anybody tell me whether it is visible?
Yes, it is visible.
Thanks again.
Yeah.
So for this session, okay, so as you know, my name is Prajwal Nandekar and I'm a senior scientist working with Schrodinger Bangalore office. So just in case if you want to discuss more about the software or usability, or whenever you come across any problem, you can note down my email ID, which is prajwal@schrodinger.com, and the phone number. It's pretty simple to remember. So okay, so I mean the thing is, in our previous sessions by Schrodinger, you have already came to know about structure-based drug designing or structure-based virtual screening using molecular docking. So molecular docking with Glide software. So you are well aware of the procedure, how to do it, and what are the steps involved in it, and what is the basics of it. So if you still haven't gone through the webinar video, you can check it out, the video on 22nd July at 6 p.m. So that includes everything you need to know about molecular docking, the basics of molecular docking, and how to use it with Schrodinger software. So today I'll be focusing on the induced fit docking methodology and how to do it, what is basics of it, how to analyze it, and I mean at the end you will come to know about how easy it is to do with Maestro. So basically it is just single click panel and just a single click result, which you will be analyzing it at the end. But before that, we need to know about something basic. So what is induced fit docking, why it is necessary, what are the conditions to perform induced fit docking. So without wasting a time, I just like to start the presentation on induced fit docking. In other way, you can call it also as a flexible docking. So let's start it. So far we have seen like different types of docking algorithms, which we have like high throughput virtual screening, standard precision, extra precision. So that is the in general docking methodology which we have. But other than that, there are many different type of dockings which we can perform. So just last presentation delivered by Dr. Pritesh Bhatt. So he has explained everything related to the extra precision molecular docking and how to analyze it. And today I am focusing on induced fit molecular docking. So how it works basically. Other than that, we will have a few more sessions on very other type of dockings which are listed here, and that will be, you will see in consecutive sessions. So let's start about it. So before that, this is very well known slide which I always present, just to give a brief intro of what is like how drug binds to the target, what is a model it follows, like it follows lock and key model. And the drug designing is all about finding a best key out of many millions of keys which are available in the universe. So by using computational methods like various softwares, even we can try to find out the best key, and that best key is basically our lead molecule or our drug molecule. So the thing is, in lock and key model, it's very simple model because our lock is statics. But in our biological drug designing, you can see like whether your lock or receptor is really a static one or not. That is the critical question, and the answer is simple. It is not static. Just like it is not just like lock. It is always, it has its own dynamism, and you need to deal with that dynamic structure. So how to deal with such a dynamic receptor? So far we have seen general molecular docking, which we consider it as a flexible ligand and rigid receptor. So we have gone through all that process, how the ligand is present and how receptor is present, and how it samples various conformation of ligand inside the binding pocket of protein, and then it assigns score to each pose, and based on scores and interactions we define like which is the best molecule out of our data set. So that's called in general docking. But here the main thing is our receptor is considered as a rigid, but in biological environment there is nothing called rigid, it's all flexible. So if you see like protein, overall protein, so protein is always present in dynamism, and it can have various conformation just like this man. So basically this man is, though it looks static, but it is not at all static. It can have various conformations around various residues, various loops, various substructures. So those all are also we need to consider if you want to see this man alive. So same thing is applicable to our protein also, protein and protein binding pocket specifically, because we are dealing mostly with the binding pocket. So binding pocket can also have different type of conformation, or it can have various sub pockets which are present always in it, or which you could consider it as various allosteric pockets, or other than that various channels or tunnels. It can have different type of breathing motions, just like other protein like actin proteins has various breathing motions, or HIV protease protein also has different type of breathing motion. So there are many different type of motions which are present in the binding pocket, which governs the binding pocket size, its volume, its shape. So, but in our traditional docking, we normally don't consider their various shapes and volumes. We just consider it as a static and we proceed further. But there are various levels of flexibility which we can consider in molecular docking or in drug designing, computer aided drug designing method. So first method is rigid receptor docking, in which protein or receptor is rigid but ligand is flexible. Ligand can have various conformations which is sampled by basically molecular docking program, and it gives you the best fit based on scores or interactions out of it. So other method is induced fit docking method, which we are going to cover today. So basically in induced fit docking, the binding pocket residue, specifically where ligand get bind, we consider this binding pocket as a flexible. Here, as you can see in this video, the loop is moving, and amino acid residues basically which are present in binding pocket are also flexible. So basically we consider protein, not the complete protein as a flexible, but the binding pocket is considered as a flexible, and ligand is always flexible. It can have different conformation, same as that of amino acid residues present in the binding pocket. And third level of flexibility is, of course, molecular dynamic simulations. So in molecular dynamic simulations, basically your complete system, including protein, ligand, solvent, ions, and everything else is considered, all things are considered as a flexible. And this is basically a movie from a paper by D.E. Shaw, and it is very kind of revolutionary paper that time in 2011. So basically in this paper, basically they have simulated this complete protein ligand system for a few microseconds, and they could able to sample the all possible conformations of ligand in various binding pockets of the protein, and finally your ligand gets stabilized in the actual binding pocket. So though protein can have various pockets, cryptic pockets or allosteric pockets, but still ligand finds its place and gets stabilized in microsecond of simulation. So in this specific in this presentation, we are specifically focused on induced fit docking, but in consecutive presentations we will be also focusing on molecular dynamic simulations afterwards. So let's start with induced fit docking. So basically, what are the advantages of induced fit docking? So mostly is this is basically a surface view of protein in which you can see like there is a binding pocket and ligand present inside it. And this is a traditional molecular docking in which basically receptor is a static one. So that's why, I mean, there is no change in binding pocket upon ligand binding, because we can't consider that flexibility of receptor in traditional molecular docking. But in case of induced fit docking, as you can see here, as there are various conformations of ligand which are present inside the binding pocket, accordingly the receptor binding pocket also adopts various shapes and various sizes. As you can see here, because of flexibility of those binding pocket residues which are there, so because of that flexibility, it continuously changes the structure or size or volume of binding pocket substantially, and that is all induced because of the size of ligand or interactions which are made by ligand inside the binding pocket. So these are the minute details. Basically, I would say these are the details which we capture in induced fit docking, and those details are absent in traditional molecular docking. So that's why we consider it as a one level higher theory for computer aided drug designing, in which we consider protein as a flexible, a binding pocket as a flexible. So the thing is, this is the reason why we, if it is possible for us to go into more detail, then definitely one should go for induced fit docking to get a more detailed insight about the binding pocket conformation and the probable binding orientation of ligand. So according to on the study, it was observed that around like 50% of your docking cases is require some degree of freedom, not only to the ligand but to the binding site residues. So you can see here like this phenylalanine, which is present in stick representation, has different type of conformations, and according to those different type of conformation of phenylalanine, the basically ligand acquire different conformation inside the binding pocket. So that's the reason why at some point one need to consider induced fit docking as a methodology in their computer aided drug designing protocol, because we wanted to see like why because of flexibility of those residues, active site residues, how the ligand conformation get changed, and that is near to the realistic conformation of protein. So one of the example is means why it is required is there are two protein structures in protein data bank. One is 1ERR and another is 3ERT. Basically both are the crystal structures for the same protein called estrogen receptor. And so basically in one ERR structure there is a native ligand which is raloxifene, and in 3ERT structure there is another ligand which is tamoxifen. So what they did, you can see here in the yellow color, it's a 1ERR structure, of estrogen receptor, in which ligand is particularly present in particular orientation in the crystal structure. But what happened when we dock the same raloxifene in the another crystal structure of same protein? That ID is 3ERT, which is shown here in the cyan color. So ideally, it should reproduce the same pose because the protein is same, though the structures are different. I mean, the crystal structures are different, but the protein is same. But what happened after doing normal traditional glide docking, the docking could not able to sample the exact conformation of raloxifene in the protein 3ERT. And you can see like how this yellow color raloxifene and cyan color raloxifene are superimposed on the top of each other. They are not looking exactly because of lot of reasons, because of different because the crystal structure is different. So that's why the conformation of amino acid residue is different. That you can see here, the cyan color loop, which is a little bit diverted than the yellow color loop. So you never know which is the correct form of protein structure, but because of flexibility in this particular region, so it has different conformation of proteins, and which is same implemented in the binding pocket. So you can see the RMSD is around 7.49. So I would say like this is not at all acceptable if you want to basically generate the exact pose of ligand inside the binding pocket. Means this is the results are, I would say it is not reproducible in terms of exact pose. So how to deal with such problem? Because this is very day-to-day problem, because you know, in protein data bank you will have millions of structure available, and for each protein you can have multiple crystal structures available. And if you see all those crystal structure, every crystal structure can have different conformation of amino acid residue. So one need to seriously deal with such problem, and we need to consider like which protein structure I should go further with. So for that, we have the best answer with us is called as induced fit docking. So if you don't want to go for MD simulations, then induced fit docking is the answer. But the ultimate answer is molecular dynamic simulation. But here we will see like whatever is possible with our let's say i5 computers, if you have. So to perform induced fit docking, you really don't need high performance computing clusters or GPUs. You can do it with your normal i5 machine also, if you have Schrodinger software. So basically what it covers, so this induced fit docking algorithm basically covers the traditional glide for molecular docking and conformational sampling. Other than that, it also use prime. The prime is a module which is required for basically a model building. Model means protein model building. So you basically it tries to generate various conformation of that loop or that residues which are present in the binding pocket, and with the glide it docks the ligand inside it. So it is also having high accuracy for your molecular docking, as well as lot of flexible your targets. You can consider those you can consider this methodology for those targets which are highly flexible in nature. Again, if you don't want to go for MD simulations, then I mean, it was also observed that in case of ligands which are tested for this testing of induced fit docking method, most of the ligands have RMSD less than or equal to 2 angstrom. So that is again acceptable range for the result reproducibility. So that's why I would consider like induced fit docking is one of the better methodology in computer aided drug designing protocol. So what is in the algorithm of this molecular docking? So simplistically, if I tell you in simple way, is it requires the receptor and ligand. So receptor can be your crystal structure of protein, and you know the crystal structure of protein is a rigid structure. So we take it as a rigid structure, and your ligand. So basically you can see here you have green color receptor and red color ligand. So basically it performs simple molecular docking of our ligand molecule inside the protein structure wherever we have specified the binding pocket, and it tries to generate various conformation of ligand inside the pocket, but with soft potential. So soft potential means this algorithm allows ligand atom to overlap with the protein atom to find the best possible way how it can fit inside it. Once you can see here, like your red color ligand is always overlapping with the green color protein structure or residue schematically. So even you will have those overlaps. So those are considered as a soft potentials for amino acid residues, and then it performs the prime refinement. Prime refinement means the protein structure refinement, so refinement of those residues which are basically overlapping with the ligand molecule. So it basically it refine those residue by performing energy minimization of those residues and try to accommodate your ligand perfectly, and accordingly it scores it sees it check that how this binding pocket looks like after performing this refinement of amino acid residue, and in that binding pocket it again try to redock all those ligands which are present in each binding pocket, and afterwards it gives scoring and try to accommodate ligand in best possible way with different binding pocket conformation. So at the end you can see ligand can fit inside the receptor in this way, or it can completely present or buried inside the receptor in this way. So that's what the simplistic representation of induced fit docking algorithm. So in total, like it basically allows the protein binding pocket to get refined to explore various conformation of amino acid residues, and in this way it tries to see which are the other possible conformation of residue and how it looks inside the binding pocket, and how the binding pocket changes the shape because of induction of ligand. So that's what is present inside the induced fit docking algorithm. So when it comes to the actual case study, we can see here there is one case study of thymidine kinase protein, in which we have basically two crystal structure. One is 1Ki4 and another one is 1Kim. So let's start from here. In brown color you can see on the left hand side image, we have basically this ligand molecule which is 5-bromothionyl deoxyuridine. So basically it is present in co-crystallized form, and you can see like it has interaction with tyrosine 101, then glutamine 125, and there is also amino acid residue present which is tyrosine 132, and this ligand is perfectly placed inside the binding pocket of crystal structure 1Kim. And there is another crystal structure of the same protein which is called as 1Ki4. So in that crystal structure, basically another ligand is present inside it, and you can see the difference between two ligand is this extra 5-atom ring structure which is present inside in the ligand. So because of presence of this ligand, basically the position of tyrosine 132 residue is shifted little bit as compared to the brown structure which is 1Kim, and you can see this happens because of presence of this extra additional group in the ligand. And now we want to reproduce the same thing if we dock this 1Ki4 ligand which is cyan in color in the brown color protein structure. So whenever it docked, so you can see here like we have docked this particular ligand of 1Ki4 in the crystal structure of 1Kim, and you can see it perfectly reproduced the orientation of tyrosine 132 which was slightly away because of presence of this additional group which is present in the ligand. But at same time it also retains the original interactions with glutamine 125 and tyrosine 101 and glutamic acid 225. So those kind of interactions are still retained, and the position of tyrosine 132 residue is same as that of the initial structure, means slightly away, whatever we have observed in the protein structure called 1Ki4. So this is how it would able to reproduce the same information which is present in different crystal structures because of different ligand molecules which are present in the binding pocket, and because of those ligand molecules, various size of ligand molecules, various functional groups which are present in ligand molecule, there are many conformational changes that could happen inside the protein structure and specifically in the binding pocket, and those exact conformational changes are captured through induced fit docking methodology, and at the end this IFD docking could able to generate a ligand pose which is exactly same as that of 1Ki4 with the conformation of tyrosine 132 residue, and it has a RMSD of 0.4, which is which itself says like the pose is exactly retained. So similar way, in another example, we have two structures from antibody DB3 and its PDB ID is 1DBB and 1DBA. So basically 1DBA is a apo form of receptor, means apo means without ligand which is present inside the binding pocket. So there was no ligand present in it. So because there was no ligand present in it, so there were different conformation of amino acid residues which are observed inside the crystal structure. So one of that conformation is tryptophan 100. So you can see here tryptophan 100 is perfectly present in horizontal position in this image. And when we docked the ligand from another structure called 1DBB. So before that, you can see here in cyan color, there is the same antibody with different crystal structure. This when the cyan color ligand, which is basically a progesterone, when that ligand is present inside it, there were few interactions as like aspargine 35. That interaction is present with it, but you can see the position of tryptophan 100 is now in horizontal position. So it happens because of the favorable interaction between tryptophan residue and progesterone molecule, which is shown here in the cyan color. So other thing is, you can see like there is a histidine residue, and this histidine doesn't have any contact with this oxygen atom of progesterone, but ideally it should form the hydrogen bonding because the conditions are favorable. So what we did is we docked this cyan color ligand which is present in the structure called 1DBB. We docked it into the apo form of protein structure which is 1DBA, and at the end, by using induced fit docking methodology, you can see like in the green color, when we dock this ligand, the position of tryptophan 100, which was initially present in horizontal position, now it becomes vertical, same as that of the ligand bound crystal structure called 1DBA. So means it could able to reproduce the same conformation of amino acid residue tryptophan 100 by using this molecular docking methodology, induced fit docking methodology. And also it also optimized the interaction between histidine residue and progesterone oxygen. So in this way, it itself says like how this methodology works, and you are able to reproduce the same type of crystal structures which are already solved. So that is called as a control in our computer-aided drug designing methods. So one of the classical example is with estrogen receptor with the protein called 3ERT, and which is ligand bound structure, and another structure of same receptor we have its ID is 1ERR. So basically this is what the same example which I have shown earlier, like raloxifene and tamoxifen. So you can see here in 1ERR structure we have brown color ligand. So basically this is tamoxifen molecule. It is a raloxifene molecule which is present inside the binding pocket, and which is having various interactions with histidine and then glutamic acid and arginine. So it has different type of interactions which are present with raloxifene. And when we observe the same protein with different crystal structure called 3ERT, and this time ligand gets changed to tamoxifen, and you can see like it has it retains the same set of interaction, but the position of particular residue called histidine 524 is changed. Again, it changed because of presence of that particular ligand and the favorable interaction with the ligand molecule. So, but when we dock this tamoxifen ligand into the 1ERR structure, which was initially present with raloxifene molecule. So, because of that induction of this ligand molecule tamoxifen, it could also generate the same conformation of histidine as that of which is present in 3-ERT with tamoxifen as a molecule. So you can see the position of histidine is now very well oriented like as before, and while retaining all those interactions which were previously present in the 3-ERT structure. And you can see additionally there are some intramolecular or inter-residue hydrogen bondings which stabilizes the receptor. Those are also found between arginine 394 and glutamic acid 353. Basically, those interactions were absent in the crystal structure, but after doing induced fit docking, somehow it generated various conformations of amino acid residues in the binding pocket, and somehow it stabilized this ligand molecule with all those hydrogen bonding interaction. So this is also this is also one of the classical example which says if you do cross docking of the same or different ligand in same or different crystal structure of the same protein, you could able to reproduce the conformation of those different crystal structures. So that itself says like this how this methodology works and why one should consider these methodologies in their virtual screening protocol. So in this way, actually, there is a paper in chemical biology and drug discovery. So in 2006, they have screened various proteins and their structures, and they perform this type of cross docking from ligand from one crystal structure to the ligand in another crystal structure, and they perform it with the normal glide docking, which is rigid receptor docking, as well as induced fit docking. And as a result, you can see like for most of the test cases, they have RMSD value less than 2 angstrom, and which is perfectly fine in silico methods. And you can see most of the time they were able to reproduce the pose of ligand from one protein into another protein. So, and in same way, you can see like how this methodology work as compared to rigid receptor docking. You can see this graph which are represented in dark color are most of the time like on x-axis you can see RMSD values, and y-axis it's a count, and you can see within 1 angstrom RMSD you can have more than 8 cases, and if you increase the RMSD range to 2 angstrom, it will further increase the number of cases which are perfectly which are able to reproduce the exact pose of crystal structure, and in this way it goes on. So at the end you can see percentage of poses which are predicted for less than 2 angstrom RMSD. So in induced fit docking, more than 95% of time it perfectly predicts the poses within 2 angstrom RMSD. But in case of rigid receptor, the statistics is pretty poor, like less than 20% it could able to predict. So it works whenever you have different conformations of the structure for same protein. In that case, one need to consider this methodology to see to get a better result or better binding pose of a ligand. So the question comes like, when do you need to consider this induced fit methodology? So there are a few points which one need to think of before proceeding for induced fit docking, like why you need to perform it. So one thing you always need to remember, whenever you need to remodel the protein structure. So remodel the protein structure means you want to generate various conformation of amino acid residue or generate various conformation of loop. Means because these are the elements of protein structure. So whenever you want to remodel it, whenever you want to generate various conformation of protein structures, it is computationally intensive process. So it would require a lot of time as well as CPUs. So that's why it is expensive than normal glide docking, means rigid protein docking. So that is one thing which you always need to consider, that it would take some time. So one need to be patient to get results, and you can't really do this task for millions of compound. You can perform induced fit docking for few compounds, let's say 10, 20 or 30 compounds, which you think these are potential and that might affect on the protein conformation. The another thing is you also need to know like whether your protein is flexible or not. I mean, there are a few examples in which there are, let's say, multiple crystal structures of the same protein is present, and all structures have same type of conformation. Means exactly same conformation of amino acid residues, even in the binding pocket. So in that case, there is nothing much flexibility is incorporated in it. So we can, so it is not really necessary to perform induced fit docking. But there are many proteins, just for example, kinase protein. Kinase protein has a classical DFG loop, which can have in and out conformation and many other. So you can see like because kinase protein, same kinase protein can have multiple structures and each structure has different conformation of amino acid residue. So one need to know like which conformation of the binding pocket I should take forward for my virtual screening. So in that case, we can perfectly use this induced fit methodology. So we need to consider the flexibility point of the protein. So again, we normally consider it as when we know like the binding pocket is small and there is a large ligand which is which fits inside the binding pocket. Let's say you know it from experiments, or you know there is a one large ligand molecule which is active against this protein, but you don't have any crystal structure for this particular large ligand inside the protein structure, protein cavity. So we can use such induced fit docking methodology, and we can try to induce some motions in the binding pocket and try to change the shape of binding pocket as per this large ligand conformation. So because of this large ligand conformation, it tries to generate space inside the small binding pocket, and because of that generating extra space, the binding pocket becomes larger. And in this way, we can optimize the different conformation of binding pocket because of presence of large ligand. So that in such case, you can perform induced fit docking. Then another thing is, if, for example, if you know there is one ligand which could bind to the protein structure, and that information you know experimentally that yes, it binds, but your rigid receptor docking, means normal glide docking, is not able to capture that particular position, that particular conformation of ligand, or it is not able to dock inside the protein structure. In such case also, you can use induced fit docking methodology by forcefully docking the ligand inside the binding pocket and expanding the volume of binding pocket. So that you know. So other example is, for example, I have given example of kinase structure, in which you know, like from experimental structures, you can say crystal structures, you know there are large number of variations in the conformations of binding pocket residues is present. So in such case, because of various conformation, you never know which crystal structure you should go further with. So in that case also, you can perform induced fit docking. Or another way of analyzing that flexibility is beta factor. So that beta factor is normally present in the text file of protein data bank, means the file which you download from protein data bank, that protein structure has beta factor values, and you can see by using beta factor values, you can see whether these residues are flexible or not, whether it has a profound electron density, or electron density is not certain in particular region. So if such things are present in basically binding pocket, so you can basically use this induced fit docking methodology to get the exact conformation of protein as per ligand present in it. So other than that, it is very critical, like whenever we have a apo form of protein structure, means for example, you have a protein, some XYZ protein, and it has a only single crystal structure which is present with the protein, and there is no ligand present in it. So we can say it is a apo form of protein structure. So in such case also, because there is no ligand present in it, but for somehow you know the tentative binding pocket, but because ligand is not present in it, so somehow it doesn't give you the exact conformation of binding pocket in the crystal structure. So in that case, you can use this induced fit docking method to find out the exact shape of binding pocket residues in presence of this ligand. Or same thing can be applicable to in case of you have homology model, which is which you have built without ligand in it. So in that case also we can use this induced fit docking method to generate a profound binding pocket. So these are the various conditions which you need to look for before proceeding for induced fit docking. So in that you can use it. So the induced fit docking panel, if you see, it is pretty straightforward. So it is just a single panel which is in front of you, and it just two click. There are only two clicks which you need to click on, and that's it. So first thing is like you need to provide your ligand molecules which you want to dock. Second thing is you need to provide the box center. That can be your center of co-crystallized ligand present in it, or you can specify it from the residues which you know these residues are binding pocket residue. It's the same as that of grid generation panel, if you remember. So just two things you need to give. And the second thing is by default there is a factor of I mean 5 angstrom residue surrounding residues which are present around the ligand, that those are considered as a flexible residue, because those are the residues which mostly present in the binding pocket, which comprises of a binding pocket. So basically this is by default parameter which is present. You don't need to change it if you don't want to change. So that's it. Means you need to provide ligand, you need to provide grid center, and click on run. So this is just a 2-button thing. Once it runs, it gives you the results. So you can analyze those results, and we will see how those results we can see it in a Maestro. So before proceeding to induced fit docking, one thing you always need to remember about the Maestro interface. So there are various buttons which are present on the Maestro interface. These are various elements. For example, there is a list of entries that we call it as a workspace navigator, then structure hierarchy section, then this middle dark region is basically workspace, and where you can see your molecule or any model. Or there are style button, preset buttons, or build edit, where you can change or build the structure of molecule protein. And there are many other selection modes and task bar where you can see basically where are other modules present in it. So these things are pretty well described in our previous presentation, which is on 22nd of July. You can always go through that presentation which is present on YouTube, and you can see how to browse through all those features of the Maestro. It is pretty user friendly. And other thing is which I always say, whenever you have protein structure with you from any source like database, or for example protein database, data bank, or any other source, you need to go through protein preparation wizard. So this is the panel for protein preparation wizard. It is also pretty straightforward. I have already explained it in previous video how to go through it. It just 3 clicks you need to do, and your protein will be prepared. So you need, for any protein structure, you need to go through protein preparation wizard, and for any ligand structure, you need to go through ligand preparation lig prep panel. So it is also single click panel. You just need to load your structure and click on run. That's it. So and these all things are pretty well explained in my previous presentation on on this molecular docking, which is already streamed on July 22. So you can check it out and see it in detail. And that's it. So next thing I will show you the demo of how induced fit docking works in the Maestro. So for that we just need to start Maestro. This is the icon. You just need to double click on it, and it will open the Maestro visualizer for you. Once you will have this visualizer, the very first thing you need to do is change your working directory. So that is present in your file menu. Change your working directory to somewhere wherever you want to save your data. So I have chosen the directory and just say choose. And the thing is you need to save your project so that you should not lose your data or visualization points. So just there is an option in file menu, save project as. So just give some name to your project and save it like that. So once you save your project, we need to load our protein. And as I always say, like whenever you have structure with you, protein structure, it is always necessary to go through protein preparation wizard. So here you can find a protein preparation wizard in protein preparation and refinement section. So here you will have protein preparation wizard panel. So just you need to go through first panel called hello. Hello, am I audible?
Prajwal, yes, you're audible. In between, we lost your audio. Yeah.
Yeah. Okay, I'm audible. Yeah. Sorry for the interruption. Actually, we lost electricity, so everything was down. But okay. So let's resume the point. So Giri, can you tell me that I'm audible and you able to see?
Yeah, you're audible as well as we can see your screen. Yeah.
Okay, thank you very much. So as I said, like whenever you have protein structure, you always need to go through protein preparation wizard panel, and just using 3 clicks, you can you can perform protein preparation on the protein structure, which is a pre-process, and this pre-process button, then review, modify, and refine button. In refine, you have optimize and minimize. So just these 3 clicks, and you will have various entries generated, in which your final entry is the minimized protein structure with you. You can basically highlight the ligand wherever it is present on the structure by using this preset button. So you can use this button to highlight you wherever your ligand molecule is present. So once you are done with the protein preparation, whatever ligand you have, similar way you need to go with the ligand preparation. So for that we have leak prep. So you can see here, you whenever you have ligand, you need to go through ligand preparation, and in ligand preparation we have option called leak prep. So that is also just a single button thing. So you just need to provide your ligand molecules and click on run, and it will take care, all things are being taken care of. So once you will have ligands with you, so now we are ready for the induced fit docking thing. So for that, let's say you have protein with ligand which is present here, and now we will try to look for where the induced fit docking option is. So basically you need to go to task and browse, and in browse you will have another option called induced fit docking. So in induced fit docking we have this option called induced fit docking. So just click on this option, it will open the panel. So as I said, like it is pretty straightforward. You just need to give the ligand file wherever it is present. Let's say I'm giving it from file. So I have already prepared some ligands. So I'll just give it as a input. So that's my ligand, which is output file from ligand preparation. So that's what I have given. Then another thing is I need to provide box center. So for that, it asks me to choose centroid of workspace ligand, and here is the button called pick. So I just need to carefully pick on any atom of the ligand, just like the same as that of grid generation panel. So once you click on it, it automatically identifies this ligand as a grid center, and that's it. So that's it. You can go with run, or if you want to see another option called prime refinement, which I have shown you. So basically by default it considers residue which are around 5 angstrom from the ligand are flexible residues. So you don't if you don't want to change the 5 angstrom, it's fine. In case if you don't have ligand present inside the binding pocket, then also you can go with the next another option called centroid of selected residues, and then you can specify various residues which you think which are present in the binding pocket. So that's it, and click on run. So once you click on run, it runs the induced fit docking job. But again, as I said, like it is time consuming things because it involves lot of conformational search for the protein residue. So it is pretty time consuming. So I will show you the job which I have already run. So basically it generates the output in some format, and that we will see like how it is present inside the folder. You can directly go to file, import structure, and look for the directory wherever you have specified for induced fit docking job, and their name must be starting with induced fit. And you can see here there is a folder called induced fit, and inside that folder there is a file called the job name -out.mhz. So that's your final file. So you just need to open this particular file in the Maestro, and that's it. So once you open this file, it will load all of your results into the format, and you can see like here you have molecular docking results loaded, which is a pretty big list which consists of around 283 entries. Means because these are various conformation of the protein as well as ligand, that's why you have many conformations and many poses of ligand present in it. So as just like any other molecular docking result analysis, you can analyze it in a simple way by using preset button, and you can use this apply custom preset and see all type of interactions which are present between a protein and ligand. So you can see whether there are hydrogen bonds or pi stacking interaction or any other type of interactions in 3D view. If you are not satisfied or if you don't feel comfortable with 3D view, we always have 2D ligand interaction diagram that is called as ligand interaction button. So if you simply click on it, it will display the same interactions in 2D view. So this is what we have already seen in molecular docking exercise, and we have well explained there how to see these interactions. So these interactions are already present here and you can see it. But there is also another way to see it, which you can basically probably you will like that how it is present here and how you can see whether ligand is flexible or protein is flexible. So you just need to select all of your entries from output result. Just go to project table, and in project table you will have the play button. So this is just like the same YouTube play button. You just need to click on this button and it will automatically go through all those entries which are present there. And here basically you can see not only your ligand is flexible, but your protein is also flexible. How this loop moves and how it accommodate various position based on the ligand conformation inside the binding pocket, and that you can easily see like how these interactions are changing, how the position of ligand is changing, and how the conformation of amino acid residue is changing. But at same time, if you see the other part of protein is still rigid, means we have not imposed any flexibility in other part of protein except the binding pocket residues. So this is the way you can see these results, and based on these interactions or binding pocket volume or the size of binding pocket or the final score, IFD score, which you can see in the project table. So based on that score, you can decide like which is the best protein conformation for me. So another way which I really like to see it in a surface view. So for that, let's say I have generated surface for all of those entries with me, and we'll just see like how it looks like in surface view. So yeah, so surface needs to be highlighted, but right now it is not present. But you can see like in the presentation how this surface view works. So I just show you one more time how this analysis is. So for example, here it is given. So you can see this particular image in which the protein is represented in surface view and binding pocket is present, and because of ligand, binding pocket can accommodate different shapes and size. So this is the way. This is also one of the. So other than that, if you are interested in looking at particular scores, so those scores are also present in the project table, and we'll just see those scores. This is called as IFD score, and these are the scores. So basically, you can see the various scores like docking score and IFD score. The more negative value is better. The pretty straightforward, and based on score, you can check like which one is the best possible conformation of protein binding pocket and the ligand conformation for you. So these are the two ways to analyze these induced fit docking results. And with this, like I'm just about to conclude the session. At the end, I would like to show you this help button. So that help button is always there to help you out with any type of query. You just need to click on help and just search your query, whatever is possible. And it will give you all possible information related to the software, tutorials and manuals, everything. So with this, I would request you to, again, you can register yourself on the Schrodinger website. Just go to www.schrodinger.com, register yourself, and then once you register yourself, you will have access to all online available information or material available with us, so that you can access. It has various tutorial videos or training videos, or other articles like knowledge base articles, means which could consist of various queries, and those were answered by the experts. So that all information is present. Just give a try and check it out if it is helpful to you. I'm sure it is really helpful to you for your actual projects. So with this, at the end, I would like to acknowledge my team, which are located in the Bangalore office, and everybody is really working round the clock to help you out for your projects related, all helps related to the Schrodinger software. So with this, again, I would like to say thank you to all of you for listening it carefully, and I hope I am within the time. I did not take your much time, like 2 hours. And again, I would like to open the session for questions if you have. At the end, you can also note it down my email ID in case of any queries if you want to ask or discuss. So with this, again, final thank you to organizing team Drug Discovery Hackathon 2020, and thank you to Giri for hosting the session. Thank you very much.
Thank you, Prajwal, for the insights in induced fit docking. So we have a few questions. Shall we go to the question answer session?
Yes.
Okay. So one is, how can I build the pharmacophore model for a particular protein?
Yes, that's a great question, but I would say early, because in next sessions we will have, say, a webinar on pharmacophore mapping also.
Okay.
So I request you to follow those sessions, but yes, it is possible. So we have a module called phase, in which you can build a pharmacophore from the available information of protein structure. So we will cover it in a detail.
Okay.
Please.
Another one
please.
with a question is with a scenario. Like if I wanted to target a protein X, but there is no co-crystal structure present like an inhibitor. Its selective inhibitor might be present in another protein Y. So both protein X and Y could be from same class or not. So in this manner, how can we compare the protein, or do you have any features to make them understand how these X and Y is related?
Yeah, I mean, this is again the, I would say, classic example of induced fit docking. So if your protein belongs to the same class, let's say, let's take an example of kinase protein, which can have different isoforms. So your protein X belongs to one isoform and protein Y belongs to another isoform of kinase, but the ligand, I mean, the co-crystallized ligand is only present in Y structure. So you can basically get that inhibitor molecule and dock it using induced fit docking, inside the protein X and see how the binding pocket conformation gets changed because of accommodation of that particular ligand, and that could be your the answer of this particular exercise, that how it binds.
Okay. Another scenario, like, can we apply induced fit docking when the ligand would not bind to the active site of the target?
So if ligand doesn't bind to the active site, so maybe you mean active site means orthosteric site, and probably you are looking for something else called allosteric site or cryptic site. So if such a case, then yes, you can use a induced fit docking method to dock it in any other pocket which is possible in the protein structure. That can be your allosteric site, that can be your cryptic site, that can be your transient site. So you can use this methodology.
Okay. Another scenario, it's too much of scenarios anyway. I hope you will be able to take it up. So there is one apoform of the protein structure. I mean, there's only apoform of the protein structure. And if the user knows the active site and the selective inhibitor, but there is no idea which water molecules could be so important. So how can the user build the SBPM? Sorry, I don't. He has not mentioned the expansion for that. He is abbreviated as SBPM.
Structure based. I'm sorry. I also
sorry,
don't understand
the question is already
but
there.
To know the water molecule.
Correct.
Sorry.
Yeah, exactly. That is the question there anyway. Which water molecules will be important? How to get?
Yeah. So I mean, it's always debatable, like how to see whether water molecules are important or not. But in my understanding, if your water molecule is a bridging water molecule, bridging means if it bridge between amino acid residue and the ligand present inside binding pocket. If there is such water molecule present, then definitely it is very important one. And basically we need to check it. So the best module so far I know is water map, so which includes MD simulation also. So that using water map module, we can easily check by using energetics of the each water molecule whether it is important or not. Other thing is visual inspection, and one need to try it in various various way of docking, that whether this water molecule is really important for ligand placement or ligand interactions.
Okay.
But I would say water map is the answer.
Okay. And in this induced fit, is there any module or some features that can automatically generate analogs from the compound that is docked, or if you're submitting some compounds? Is there any feature that it can generate some analogs automatically?
So the answer is, I mean, induced fit panel is specifically for the induced fit docking. But there is another panel which is called as enumeration, and in that you can generate millions of analogs. I would say millions of analog just by single click. And that has also shown on the presentation which was on 22nd of July. So you can please go through it and it will show you how to enumerate a molecule, and that molecule you can use for docking.
Okay. Another question is, is there any? Okay, so the person who was asking about SBP, it was structure-based pharmacophore.
Structure-based pharmacophore. Yes, I mean, I would say that's really great question then. So there is a paper on such a structure-based pharmacophore using water molecules. So again, that paper is by Schrodinger also. So the thing is, I mean, yes, it is possible. So you can have different protein ligand complexes with water molecule present in it, and with this complete complex or structure, we can generate a pharmacophore in which we can include water as a feature, which can be hydrogen bond acceptor or hydrogen bond donor feature. And then based on that feature, we can generate a pharmacophore and we can screen the library of compound, and we can see like how much the enrichment you will get because of presence of water feature. So that's the best way.
Okay, great. Thank you so much, Prajwal. We are done with all the questions, and thank you so much for patiently addressing all the questions. And looking forward to your next session tomorrow. And I'm so thanking you as well as all the members of the drug discovery training team from NIST, especially headed by Professor Narahari Shastri, who is the director of NIST, as well as Hruday, Nagamani, and other team members, including Lijo, Himakshi, and all. So in this slide, I also wanted to emphasize that as I'm sure that most of you have started on problem statements, so there are a few guidelines for the problem statement as well as resources which could be useful as a data for you to do analysis and generate other analysis part of your problem statement. So tomorrow, as I said, there will be a session by Dr. Abhay Jere at 11 a.m. In his YouTube channel. Please do not miss it because you will have more details about the registration. And these are the official links of training site as well as the drug discovery hackathon website. And I also wanted to mention here some of there was one question: when do we get access to these kinds of softwares? So please kindly wait. So tomorrow, Dr. Abhay Jere will be able to give you more details about the registration process. So once the registration is completed, there will be other steps and procedures to be taken care for accessing to all these tools and also accessing through virtual tool room. So you will get more details tomorrow at 11. So kindly watch and live, and you can interact with him with if you have any questions and clarification. So that's all from me for today.
So Giri, I would like to make a statement.
Please.
So from Schrodinger side, tomorrow we will have a very important presentation. I would say very important topic. That's called covalent docking.
Oh, yeah.
And in COVID research, because you know there are protein structures which are with covalent binders.
Yes.
So I think that topic will be very much important and interesting to all of you. So
Yes.
please stay tuned and attend the tomorrow's topic, which will be by Dr. Pritesh, and it will be very interesting and important to you.
Yeah, you
Thanks.
said it rightly. There are certain covalent like docking. It's very important also because we saw something from poster also, some of the covalent docked molecules. So it's really promising. So looking forward to that session too. Yep. Thank you so much, Pritesh, for that. Prajwal, for that. So that's all from me today. And wishing you all a very good evening. And thank you. Bye bye.